Number 6, demonstrate why 5 to the 4th times 5 to the 7th, negative 7th equals 5 to the negative 3rd is true. So let's start with this equation. We're starting with 5 to the 4th times 5 to the 7th, or 5 to the negative 7th. We want to know why it's equal to 5 to the negative 3rd. Well, let's use our rules for negative powers. 5 to the 4th, that's got a positive power. We'll leave it as it is. But instead of 5 to the negative 7th, let's change that to a positive power. So we're going to think of it as 1 over 5 to the positive 7th. All right. Hey, I can actually look at this as one fraction, right? Because this will essentially become 5 to the 4th over 1 times 1 over 5. That I said that this should change to 5 to the 4th over 1, which is the same as 5 to the 4th, times 1 over 5 to the 7th. If I combine these into one fraction, I could rewrite the fraction as 5 to the 4th in the numerator and 5 to the 7th in the denominator. Once I've got this, what I'm mapping out is how many times I'm multiplying 5 times itself. So in the numerator, I'm taking 5 times itself 4 times. So 5 times 5, etc., 4 times. And in the denominator, I'm taking 5 times itself 7 times. So all right, let's look for common factors we can cancel out. In the numerator and the denominator, 5 appears 4 times in both of them, right? And then more times in the denominator. So when I cancel out each of those 4 5s, I end up with just a factor of 1 in the numerator, right? All of those 5s go away, but I could think of it as 5 times 5 times 5 times 5 times 1 without changing its value. In the denominator, I'm left with 3 sets of 5 multiplied by themselves. So I'm going to write that as 5 times 5 times 5. This becomes 1 over 5 to the 3rd power if I put it back into exponential notation. And then I know because of my rules of negative powers that this is the same thing as 5 to the negative 3rd. So here's a proof of why 5 to the 4th times 5 to the negative 7 equals 5 to the negative 3rd.